Hello. Hi all. Welcome you to the next session of embedded software testing. This is on the Unit 2 testing methods. Today we study about equivalence partitioning. In the last session, we had gone through different types of testing. We will just do a recap of what are the testing methods that we have done. Last session we went through a recap of the Unit 1 sessions, all the 11 sessions we had gone through, and also we defined about IV and V, independent validation and verification, and we studied about dynamic testing. We had defined several definitions of dynamic testing. Like, it's very important to understand. It's a process of evaluating the system when the system is executing. That means we do the testing when we execute the program. The other method compared to dynamic testing is the static testing. This will be done without the need of executing the embedded software system. So this will okay. So we studied about dynamic testing with a couple of definitions. Also, we know the other method of testing using the static testing, which doesn't need the program to execute. So this could be software analysis, walkthrough, inspections, etc. Also, we had gone through two types of dynamic testing at a broader level. Explicit dynamic testing, where most of the system functions are tested by means of test cases specifically designed for that purpose. Implicit dynamic testing, we do the testing based on what we have done using explicit dynamic testing. That is, the process that we had done for dynamic testing will help us in understanding or analyzing some more test cases. That is all directly or implicitly tested. And structured basis testing for dynamic testing, we had already gone through in the Unit 1. That is PM method, which has little principles. So similar approaches are aligned with the test processes, which we have defined in the beginning of the sessions, the Unit 1. Then we also studied that both are required, because dynamic testing alone may not be sufficient to completely test the embedded system. Static means of testing also is important. So both of these techniques complement each other. Static analysis was explicitly used in olden days because those days we didn't have much tools, or the tools were very expensive. So that is why we used to do static analysis more compared to dynamic testing. Nowadays, dynamic testing is more majorly that is being used and automated a lot. Wherever it is not possible, or where we need to complement with sufficient coverage and all that, so there we will do the static testing. Also, we know that the different techniques are all based on two basic groups: black box testing and white box testing. And black box testing techniques, white box testing techniques. So we are going through currently. So three broader things that we need to understanding defining techniques, strategy, test case selection methods, coverage criteria. So we detailed about test case selection methods. We know that black box testing is basically driven from the data or the functionality. The white box, we study in detail the implementation or the logic underneath the embedded software. This is the depiction of black box and white box. You can see the upper top a black box covering the functionality, white box for the component testing. So in between certain embedded systems, so they follow gray box. It's a mix of both white box as well as black box. And coming to the coverage, we had seen the formula how they do the code coverage. Total code and executed code, both of them are used in coming up how much of the percentage we have covered. So it is simple, executed code divided by total code in terms of percentage gives the code coverage. This for the white box they use. Similarly for black box, we measure the coverage in terms of requirements. The total number of requirements that we tested against the total number of requirements, that will give you the coverage in terms of percentage. And also we had outlined the differences between black box testing and white box testing. Also we underwent black box testing advantages, black box testing disadvantages, white box testing advantages, and white box testing disadvantages. So these were some of the testing aspects that we have studied in the previous session. Now moving to the today's session, elaborating different black box testing methods. So we will detail on a test selection technique called equivalence partitioning. What is equivalence partitioning? Okay, to understand what is equivalence partitioning, we need to have some background. We all know that we do embedded systems testing with the help of the test cases. We have studied test strategy, test planning, defining the test cases, given a requirement or the specification. So typically the universe of all possible test cases is so large. That means suppose we had gone through an example requirement, say 1 to 10. So we know that that system can take from 1 to 10. We know that we can define the inputs in terms of 1 to 10. But in larger systems, you may have from 1 to 10,000 or maybe even 100,000, whatever it is. So it is bound to happen such that it may become very large. So is it possible to test all these functions? So we need to select only relatively small number of test cases, because we know that it is going to work for 1, it is going to work for 2, 3, 10, and in some cases it may not work. So we need to understand what are the inputs that basically it takes. So we need to relate them in a small number of test cases. All test selection need not be required. So that is what the partitioning the number of test cases whatever we have is called equivalence classes. So the next comes the question, which test cases we should choose or which test cases we should select. So for all of these we come across in a concept called equivalence partition. This will help in doing the test case selection. Okay. Okay. So some more details. Two test cases are considered to be equivalent if we expect the program to process them the same way. That means we know for a system if we feed 1 or if we feed 2, 3, whatever it is, and we get the same result. and we don't need to repeat them. We call that as equivalent. Similarly, we group different equivalence test cases, equivalent test cases. They all can be grouped. How they can be grouped, we will study in the next session. That means identifying the sets of inputs under the assumption that all values in the set are treated exactly the same by the system of test. As I said, you feed all these values, the behavior is same, the output is same. That means we are able to test with these values. So equivalence partitioning is the most fundamental test case techniques. Irrespective of whatever the software testing you want to do, this is a mandatory testing technique that they adopt. Okay, so we identify the sets of inputs under the assumption that all values are treated and the behavior is same. The next one is make one test case for each identified set. That means we have identified the sets of inputs which behave same. Then out of that you identify one test case. The partition of the input domain of a program so that a test of a representative value of the class is equivalent to test of other values of the class. It is telling in detail, saying that the testing of one class is equal to the other one. This technique involves designing of test cases for testing classes of errors instead of individual errors. That means this technique basically identifies the design of most appropriate test case for identifying the test classes, which will result in failures or errors in a group of the system under test than of individual errors. That means if I feed one, the system is behaving a faulty way, and I am feeding two, feeding three, four different way. We identify appropriate failures or errors as a group between 1 to 10. Suppose I am going to make, I know that it is going to fail. Then the most appropriate one I am going to select it. That is what it means. So in detail further, if one test case in an equivalence class detects an error, all other test cases in the equivalence class are expected to find the same error. That means the type of error that it finds is the same. Conversely, if one test case did not detect an error, all the other test cases are not expected to find any error. That means in that group, if it is not finding one test case, other test cases are also expected to not find any error. So other definition is that equivalence partitioning helps to reduce the number of test cases and ensure that software performs the way it is supposed to do for different kinds of input. So as I said, different number of inputs we can have to test it, but it's not realistic to have all those inputs, especially the larger systems where we have a number of inputs in terms of thousands of values. So this equivalence partitioning will help in reducing that. So equivalence partitioning is one of the most black box testing technique. Basically, the underlying idea is that the input domain can be divided into number of equivalence classes. The characteristics of an equivalence class is the assumption that all values belonging to that class are handled in exactly the same manner by the program. If the assumption is true, then it would suffice to select only one single test case for each equivalence class, because multiple test cases from the same equivalence class would repeat, right? So the test is unnecessarily repeated. The result we all know. So coverage is measured by dividing the number of executed test cases. We know how much is done in terms of pass-fail count. So it is basically the number of tested equivalence classes by the total number of equivalence classes. So the workflow when using equivalence partitioning is to analyze the specification and try to identify all likely equivalence classes. First thing we do is we analyze the specification. we analyze the specification and try to identify all likely equivalence classes. So when doing this, it's important to remember that there may be dependencies between different input variables. That means we feed variables A, B, C, etc. There could be dependency between A and B, B and C, etc. So every possible input value belongs to exactly one equivalent class. If that variation is there, then we can divide further into different classes. So the final next step is to check, choose a good representative out of all these equivalence classes to form the test case for that equivalence class. So that is the aim of the equivalence partitioning identification. Okay, in elaboration of that, we probably go through different examples. You may understand better. Okay, so different views are there based on the reference that we have. The reference I had put it in the bottom. So to have a clear understanding, basically, equivalence partition theory as proposed by Ford Mayer's attempts to reduce the total number of test cases necessary by partitioning the input conditions into a finite number of equivalence classes. This we know, we analyze the specification and come up with the equivalence classes. So this will reduce the number of test cases, total number of test cases. Ability to guide the tester using sampling strategy to reduce the combinational or combinatorial explosion of potentially necessary tests. That means as part of the strategy, the next thing is we do a sampling. That means there are 100 possible way to find a good test case or find an error. So what we do is we do a sampling like 10%, 20% of that, which is enough to bring the errors or the failures of the particular system. So that will be done with the help of this equivalence partitioning. That's what it means. Okay. Continuation of the equivalence partitioning description. It's the principle of deriving the test cases, the input domain, all possible input values is partitioned into equivalence class. For all input values in a particular equivalence class, the system shows the same kind of behavior. That means the processing is same. That means the output that is expected of that, the functionality that is getting executed out of those set of equivalence class inputs are same. The idea behind this principle is that all inputs from the same equivalence class have an equal chance of finding a defect, and that testing with more inputs from the same class hardly increases the chance of finding a defect. That means we already found a defect. It won't increase any more defects in terms of finding a different defect. Instead of testing every possible input value, it is sufficient to choose one input from each equivalence class. This greatly reduces the number of test cases while still achieving a good coverage. So what we understand from the equivalence partition is that we divide the entire bunch of test cases based on the behavior that the inputs that we provide will result in the failure or passes. So we divide all of them as a chosen equivalent class. Okay. So the equivalence partitioning is basically on it is called a two partitioning. One is called valid, other one is called invalid test cases. That means the one that are going to be tested with the help of the you can say normal range or the expected way of usual behavior of the system, that is called valid test cases or valid equivalence class. Visual behavior, what is expected from the system under test. All this comes under valid class. The one that is not so usual or what is not expected when the system is running normally. I would say each of unusual behavior, it is other behavior than what is normally done when the system is executing normally. So this can be classified as invalid test cases. So two groups of valid and invalid test cases are there. These are all coming under equivalence partition. As a result of equivalence partitioning, we are going to have two types of partitioning, valid and invalid. So probably okay. So let us see equivalence partitioning forms. What are the types that we have for equivalence partitioning? So there are two basic methods or two basic partitioning that we have for equivalence partitioning. That is why it is called as partitioning. One is valid partitioning, other one is invalid partitioning. So what is valid partitioning? When we have the system running normally, that means executing normally or deployed in the field, working as expected. So the tests that will result in normal behavior or usual behavior, those are all coming under valid test cases. The inputs that with the help of those test cases will result in usual behavior or the normal range. Suppose 1 to 10 is what the system is expected to give, or 1 to 10 is what the system is expected to take input and give us a proper result, will come under all valid equivalence. The other way of testing is with the help of like negative values or the outside the boundary, so which will result in some sort of a what is it called other behavior of the normal system. So those are all coming under invalid test cases. So basically what we are trying to say is we may have see this left side you can see a number of valid test cases. These dots, blank dots are all valid test cases. Maybe we can group them something like one group is for this, group could be for this, one more group can comprising these three. This I'll repeat. So we have this rectangle box identifying all the test cases. That's what we do, right? So in that we are going to have two partitions, valid and invalid. So in valid, what we do, so all the valid inputs which will behave in the same output, we are going to define one equivalent class. This is one equivalent class, the first one. Next could be this one. The next could be this one. So it has three test cases. So we have four equivalence, valid equivalence class. Similarly for invalid also, we are going to have something similar to this, something similar to this. We are having four invalid test cases. We may having more actually, but what we do, the behavior is same. That is why the equivalence coming to picture. Then equivalence has two things. One is valid, other one is invalid. So these are the primary first level of partitioning we do. Okay. This is a bit detail the same diagram what we have seen in the previous slide. Here what we have is we define or we name each of them with some numbers like equivalence 1, equivalence 2, equivalence 3, etc. So further maybe you can change it as something like equivalence valid 1, equivalence valid 2, equivalence valid 3. Similarly, equivalence invalid 5, equivalence invalid 6. So we have 3 valid classes and 3 invalid classes. As I said in the previous slide, we can group each of this, since we don't have to repeat all the test cases which are resulting in the same behavior. So we have 3, right? So we have to cover this. The third one could be this. So we have valid 3 test cases. Similarly, we have invalid 3 cases. This space, whatever we see, all these rest of them can be other one. So 3 valid and 3 invalid. It again depends on what sort of a test cases, what is the behavior of the system. So first step is to identify all the test cases, then divide the sphere into two level of partition. One is valid, other one is invalid. So then we group valid such way that the behavior is usual and similar results are going to come. All of these are grouped. So there are 4 here in this case, 3. So we named it as equivalence valid 1, equivalence valid 2, equivalence valid 3. Similarly, we can name it invalid cases also with a unique identifier. So that's what is highlighted here. Partition value test case equivalence classes. Create a test case for at least one value from each equivalence class. That means we have 2, 3 probably. As I said, select an appropriate one which is good enough to have a repository for that particular valid or invalid class. So partition valid and invalid test case the equivalence class first, then create a test case for at least one value from each equivalence class. That is what it means. Okay, let's take an example with that help of with the help of that probably we are more clear. Okay, this rectangular box identifies 3 columns. The first one is being an input. Suppose you take this as an input. That means this is a requirement. Let's say 2 are there. Integer n such that the n takes from -99 to +99. So that is what the input it goes for a requirement. So what are the valid equivalence classes that we can arrive at, and what are the invalid equivalence classes that we can arrive at for this particular input set. Similarly, one more let's identify. This is being a phone number. Phone number will have area code which is 200 999 and there is a prefix of 200 999, suffix any 4 digits, can be there as a suffix. This is another set of test case input, and what are the valid equivalence classes for this, and what are the invalid equivalence classes for this. Any guess? Okay, the first one will take. We know that the n takes from -99 to 99. That means the system is expected to take the input from -99 to +99. So we can have number of test cases -99, -98, -97, etc. -99, -98, -97, but all are within the range, then we can have 0, 1, 2, maybe 10, 20, 30, 50, 60, 90, 99, right? So these are all it can take. That's what the input that we have. But do we need to have all this? We know that these are all valid because these first thing is these are all valid. You agree? So valid equivalence class because still it is not equivalence class. It is just a valid input value that that n can take. Minus 99 it can take, minus 98 it can take, 97, etc. up to plus 99. So these are all test cases, but we don't need to have all this. Probably we can group this again based on the system what is going to be tested. It's subjective. It could be an analog or it could be some system having a sensor or input taking different values. So that we need to understand that system, and from the system perspective, then probably decide that is the best way. But in general, we can choose a group of test cases such a way that it makes sense. Here we have 1, 2, 3, 4, 5. So that all need not have to be tested. So this will become an equivalence class. This will also become a valid equivalence class because we have identified all the valid values. So here about 5 are there, minus 99, minus 10. So two negative side we want to have with a 2-digit number, and some more we want to fit because the implementation could have some issues in terms of single digit. So that way we can divide it. Second equivalent class having minus 9, minus 1, where a single digit negative number it is taking. Then there is a value of 0. So 0 also should accept as per this input range. Then similarly we have 1 to 9, 1 and 9 on the single digit side, and we have 10 and 99. This is the maximum value. So this is a good example of a valid equivalence class. Okay, the next one, invalid equivalence class. So what could be the invalid equivalence class? We know that the valid equivalence class we have defined from minus 99 to plus 99. The one which is invalid for n is nothing but invalid test cases. But this invalid test case can be anything. It can be minus 98, minus 47. Sorry, it could be minus 100, minus 101, 102, etc. So it can grow, but better to identify few of them. Similarly, the plus side we have a 99. It can take 100, 102, 110, 200. Some randomly we need to do it. Those are all will become a sensible equivalence class test cases, but under the category of invalid. Why? Because as a normal case, it is not expected to take that. So this will become an invalid test case. That means the system is supposed to throw an error, or system is supposed to behave not usual manner. That is why it is called as invalid test case. So what are the few example invalid equivalence classes for this range? Minus 99, less than minus 99, we can specify the value such as minus 100. And other one is greater than 99, such as plus 100. Then the numbers are malformed, or the numbers are tweaked in such a way that the system will accept as a negative or unusual value, like 12 minus. Instead of minus 12, we are giving as 12 minus. Similarly, we are giving the input as 1 minus 2, minus 3. So this you consider something like a value instead of a number basically. So the system has an n, and which accepts the input in terms of minus 99 to plus 99, and the input that we are trying to provide is 12 minus. Similarly, 1 minus 2 minus 3. Likewise, we can add anything that we want. in terms of numbers. The numbers are wrongly fed. Similarly, non-numeric strings. That means instead of number, we are trying to give some character which it should not expect. Something like numeric, alphanumeric here, some special characters. So maybe you would have seen this while testing the software. You have seen password, right? So password it is supposed to expect a defined input only. It cannot change. So that is a good example of providing input. The input is supposed to be in the same manner what is being specified in the requirement. So empty value, that means this is a blank. Sometimes the blank is specified as ASCII. It's up to the specific program. So these are two valid and invalid equivalence classes example. Similarly for phone number, valid equivalence class, we know that area code 200 to 99. So we can have 555 to 5555, then 555, 555, with 555 as a prefix. Then we have 555, 555, 5555. This is another valid phone number. Then we have 200 less than or equal to area code less than or equal to 99. That means prefix we are having identified 200 to 999. Similarly, the last one being prefix itself identified as 200 to 99. So it is similar to what has been there for the N. Here we have a phone number with this range specified. So what are the invalid equivalence classes? So invalid format is 555, 5555 together. So similarly, the next one, two prefixes are there. Supposed to be one prefix. Area code less than 200, so maybe 100 or minus value. Similarly, it could be greater than 999. Then the other invalid class. So this one itself is an invalid, the format itself is one invalid class. So assume that so this is the entire group itself is one invalid class. This is one invalid. So we have similarly 4 invalid classes which are sufficient to test it. So area code with non-numeric characters such as characters or blank spaces, all this can be invalid equivalence class. So this is an example of. We'll study more examples in the next slides. Okay, now having seen this example and definitions, we will again revisit our equivalence class understanding. Two types of equivalence classes are classified: valid equivalence classes, set of valid inputs to the program. All other inputs which are not included under valid classes are called invalid equivalence classes. Okay, few guidelines for identifying the equivalence classes. First one, if an input condition specifies a range of values, suppose 1 to 100, the equivalence classes are one valid equivalence class counted from 1 to 100, two invalid equivalence class, one is less than the first count and the other one greater than the last count. Okay, the next guidelines. So this is a different sort of techniques. That is what is this guidelines talks about. The second one is about if an input specifies a set of values which are handled differently, like type of color. That means red, blue, green is an input, a set of input. Then the equivalence classes. What are the equivalence classes? So we have one valid equivalence classes for each value. That means red, then we have blue, then we have green. This is one valid equivalence class. One more invalid equivalence class we have out of this, like maybe it could be white or yellow. It could be. The other set of example. Third one, third guideline. If an input condition specifies a must be value, the character must be a letter. Suppose the equivalence classes are here basically depends on the type of the impending requirement. Like the requirement talks about the count here, so count will have in terms of number less than greater count. Here is a character, so we need to feed with a invalid character or invalid group of characters. Red, blue, green is a valid group, other one is a invalid equivalence class. Similarly, we have a must be a value sort of input condition is available. Then what is the valid equivalence class talks about is any letter you should consider. The any letter it has is nothing but a valid equivalence class. Other than any letter, or it is called a non-letter. It could be number or special character. That is nothing but invalid equivalence class. So all these are scattered here in this example. We can see where we have taken only the numbers as an input, and what are the non-numbers, what are the misinterpreted numbers. All these are part of the invalid equivalence class, and valid numbers and all within the range are called valid equivalence class. The fourth guideline: everything finished long before the task is done is an equivalence class. Everything done within some short time interval before the program is finished is another class. Everything done just before program starts, another operation is another class. That means we have a time-based requirement. Suppose in those cases, how we can define the equivalence class is what this talks about. So everything finished long before the task is done is a valid equivalence class. Everything done within some short time interval before the program is finished is another valid class. We can say everything done just before program starts, another operation is another class. That means three equivalence classes have been defined for the time related requirement. That is one guideline. That is the fourth guideline. Fifth one, this talks about a memory. If a program is specified to work with memory size, suppose the memory can take from 64 MB to 256 MB. So what is it going to take for equivalence? Then the size range is an equivalence class, because we know the size, what is the lower size, what is the higher size. Any other memory size which is greater than 256 or any other size which is less than 64, this can be accepted. You should accept, and those are all called invalid equivalence class. Likewise, we can define the equivalence partition for this sort of a requirement. The last sort of guidelines is the partition of output event lies in the inputs of the program. This is very important. So it is not just the input based equivalence partitioning. There are output based partitioning also that is possible. Due to the certain set of inputs, the outputs can be derived. So based on the outputs also we need to define. That is what it means. Even though different input equivalence classes could have same type of output event, you should still treat the input equivalence classes distinctly. What it means is we have two equivalence classes, but still it will result in same output. But based on the type of equivalence classes, we need to categorize it. For example, it may throw an error for all this as a one error, but that means we have one output, but still we want to test it because we know what input it can take. So that's what it means. So output event based on that. So one example we will take here: if an unlock variable where need to operate within the range 1.0 to 6.0. So there is a unlock input which can take or which will operate with a range of 1.0 to 6.0. So what are the equivalence classes that can be performed? The first type of equivalence class, input value for variable equal to 0.9, that is less than 1.0. Another input value for variable equal to 4.0. This is normal range because 4.0 is greater than 1 and less than 6. It's wrongly put here. It is this way. So 4.0 is greater than 1.0 and less than 6.0. So that way we can have the second set of equivalence. The third one will be input value for variable equal to 6.1, which is just outside the range, which is also an invalid class. So with the help of these guidelines, we are going to define different types of valid and invalid partitioning classes. Okay, one more example. System behavior is subjected to the following condition regarding to the input temperature. Suppose temperature lies within 15 to 40. Here it's very important is equal to is there. So it is including 15 and it's including the 40 at the outer boundary. So sometimes we have to be careful in doing the test case selection because the requirement says less than. Those are all trivial, but it is not a good practice to have a requirement specifying less than. So what will happen with equal to? So testers should not get confused. So better to mention as less than or equal to. Similarly, as a outer boundary as greater than or equal to or less than equal to, whatever the way. The equal to or greater than, less than operators are used. The number of possible values for the temperature is huge. This we can have 15.01, 15.02, 15.1, 15.2, 15.3 likewise till 39.9999, subject to the acceptability of the embedded system. So it is infinite, the value could be different. We know that we are going to have a equivalence partitioning for the sake of reducing all this. So that is what is mentioned here. 3 equivalence classes can be defined for this. Temperature is lower than 15, lower than or equal to 15. Temperature has a value, temperature is lower than 15 because equal to is also a valid class. Temperature has a value in the range of 15 to 40. Temperature is higher than 40. So 3 equivalence classes can be defined. So 3 test cases are sufficient to cover the equivalence classes. You don't have to have division because it is enough to test this condition. So invalid 2 are there, 10 and 50. Sorry, 10 and 50. Valid we have 1. It could be anything between 15 to 40. That is 35, for example. The choice of that particular value depending on the what exactly we are trying to test it. If the temperature of this sort of a requirement, it is enough to have 35. If you think that the system could fail at 35.5 or say 39.5, you can have it. We will study about that boundary value analysis in the next slides because that will complement further equivalence partitioning. So that is also an important technique. And we'll study about boundary value analysis maybe in the next class. Okay, equivalence partitioning continued. One more good example I will depict here. Let us consider the fuel level sensor. We shall set an indicator as per the below conditions. So fuel level identifies the levels of the fuel. Based on the level, it will indicate. So that's what the requirements. There are 3 requirements underneath this. If the level goes below 10 liters, it shall set the indicator to yellow. If the level goes above 100 liters or below 1 liters, it shall set the indicator to red. Otherwise, it shall set the indicator to green. So what it means here is that from 10 to 100 liters, we have the indicator set as green, and the above 100 or below 1 liter, it shall set as red. The one below 10 and above 1, it will set as yellow. So just to have an understanding of different values, I'll just repeat. So there are 3 sub requirements for fuel level picture. The one requirement for green, which talks about 10 to 100 liters. The one talks about red, which is less than 1 liter or above 100 liters. The indicator will show red. The one that is showing between 1 and 10 will indicate as yellow. So what are valid and what are invalid? With the help of this below one, we can identify invalid 0 and 1. The value which is in between or invalid, which is in red. The value between 9 and 10 are valid, but it is an yellow indicator because the requirement talks about yellow, so it's a valid. The next one, the value between 100 or less than that is green because the requirement tells that between 10 and 100 should be green, and between 1 and 10 should be yellow, and before 1 it is invalid. Similarly, the last one is we have to set the indicator as red if an invalid input is there. Invalid input could be greater than 100, which is 101 to 10, etc. So that is what is depicted with the help of this example. So this is a table. It is good to have this sort of a truth table. It is called the truth table. Why? Because it identifies all the combinations of inputs and which is good enough to identify and differentiate between invalid and valid classes. So what we see here, a truth table identifying on the left hand side, you can see a red, yellow, green as the indicator, and right hand side you see a different sort of classes. So what are those classes we have? We have class A, class B, class C, class D, identifying for different indicators. Less than 1, we have an indicator which is set in the truth table as ticked. Similarly, we have a yellow indicated less than 10. Maybe we can add another one as greater than 1 also. It is up to you how you want to define the truth table. Similarly, we have an indicator greater than 10 coming under as green. Similarly, we have greater than 100 coming under red. We can also add less than 100, greater than 10. Some more we can take it up as an exercise. So out of all this, what are the valid equivalences? What are the invalid equivalences? So we have 4 about groups here. So invalid is 0 and -1 because the requirement doesn't talk about 0 and 1 -1. So that is why it is invalid. Similarly, the other extreme of the requirement is 101 at 1.2. That is also an invalid equivalence partitioning. So we have 2 valid valid 2 equivalence partitioning 1, 2, 3, 4 up to 9. 10, 11, 12, 13 up to 100. So in this valid equivalence class we can choose something like 1, 5 and 9, or it could be just 1 is enough. Similarly, for the valid second group of equivalence class we can have 10, 20, 100 likewise. So as I said, output equivalence also can be done. This equivalence partitioning can be done with the help of output domain. That means output based testing, where outputs can vary for different inputs, and the single inputs also. There are output based testing which we need to consider for equivalence partitioning. Test cases are then derived that cover all equivalence output classes. That means we derive all the test cases which will take care of the output classes also. So similarly we'll define like the truth table we have for input for the output also. So with that we come to the end of equivalence partitioning. So we have gone through some of the equivalence classes examples. We defined the valid and invalid equivalence classes and the guidelines such as count, characters, must be value, and size, time, because majority of all the requirements will come under these guidelines. Also we went through a few good examples in terms of integer. Then we had defined two partitions, valid and invalid. We are going to identify and differentiate all these test cases under this partition. And we identified a couple of good examples for equivalence partition. We also know that output based partition we can do it. So end of the class as we do, so we have added more words. Did I miss any embedded software testing words? Let me see if I have missed anything. We can list it out. Okay, I think we have everything. So in addition to what we had, like IV and V, robustness, equivalence classes, we have today valid and invalid classes. Of course, boundary analysis, boundary value analysis we do in the next class. And we have a couple of exercise questions. What are the main test selection criteria for black box testing? So we have 3. Write equivalence class for the below. So below is the requirement. When the sensor temperature reaches less than 10 degrees centigrade or greater than 100 degrees centigrade, it sets the value alert, else it sets the value normal. So we have a temperature sensor which will indicate as an alert if the temperature goes below 10 degree or goes above 100 degree. Otherwise, it sets the value, it sets the indicator as normal. Write the boundary class values for the above with tolerance of plus or minus 1 degree centigrade. Anyway, boundary class next session. So that is the end of the session.